Hello, everyone. This is the first lecture of the probability and cryptography section of the math course. So in this recording, I will be going through the first chapter, and each recording I will try to do either one chapter or part of a chapter. So maybe I will uh, split a chapter into two sections to make it easier for you to follow and shorter. Right, so I'll be using the notes to go over, and uh, you can find the notes in Brightspace, of course. Pay attention to the updates. So sometimes I correct some errors or make small modifications. Nothing major, but just make sure that you are downloading the latest update. Um, so we'll start with the simple concept of probability. So you are familiar with probability. We use it in everyday life. When we talk about the chance of rain tomorrow, we'll say, well, there's a 10% chance of rain. This means that, well, it's not guaranteed, but it's not also out of the question. There is a possibility. And in our head, sometimes we interpret probabilities in different ways, right? So somebody will say 90% a chance of rain. This means that they think it's almost guaranteed that we'll have rain and they will dress up accordingly. Or the opposite, if I say uh, there's 10% chance of rain, people may act like, okay, there will be no rain tomorrow because the probability is small. So, but the other interpretation of probability is the frequency of things happening. So if I say, well, out of 10 days, there is one day that has rain. So the probability of rain is 1 in 10. Or the common example here, if I toss a coin, I have two possibilities here. Either I get a head or one face of the coin, or a tail or the other face of the coin, right? Everybody who tossed a coin knows that, well, you may get three heads in a row, or five tails in a row. So that the probability here is true when we have large numbers, right? So the more tosses we have, the closer to get to the actual 50-50, right? So if I toss the coin 10 times, I may not get exactly five heads and five tails. I may get 8 and 3, right? Or 8 and 2, right? But if I continue tossing a coin 100 times, I may get close to the 50-50. If I toss 1,000 times, there is a big chance that I'll get 500, 500, right? Uh, so we consider the probability here, or the interpretation. One of the interpretations of probability is the frequency of things happening, right? And we will use this concept a lot in this course. Of course, there are many applications for probability in networking. So reliability is one of them. So what is the probability, or what is the chance that a device fails, right? And what is the probability of a bit having an error, or a packet have an error, or what is the probability that packet will be dropped by a router? So all of these are concepts that use probability to study. Another application of probability is cryptography, which is what we will discuss next, right? So to start formally talking about probabilities, let's talk about the concept of outcomes, events, and sample space, right? So here, if I consider, let's say, the simple example or the simple experiment of tossing a coin. So the coin toss will result in either head or tail. These are the outcomes. All right, the event or events is the set, is a set. The events are sets of or that contain outcomes. All right, so let's represent, if the set includes an outcome, we'll represent it by 1. If the set does not include an outcome, we'll represent it as 0. So the event that head appears, so that includes the head and it doesn't include the tail. That's event. And let's call this event 1. Event 2 is the head doesn't appear, but the tail appears. That's another event, right? Surprisingly, probably, just for, something that you need to wrap your head around it, there is the event that both appear. And there is also event that neither appear. So somebody will say, well, you just said it's either head or tail. So now you're telling me that there is an event that both appear or event that none appear. Well, yes, we are talking about events here. We're not talking about their probabilities. So the probability of head, which we will represent as P capital and then head in our H in the in square brackets, the probability of head appear is 0.5. The probability of tail appears is 0.5. The probability of both of them appear, head and tail, which we'll use this symbol later, is 0. And the probability that none of them appear, right? So I'll give it a symbol later. So that also 0. So you have to differentiate between the events and their probabilities. The probability of 2 appearing at the same time is 0. The probability of tossing a coin and nothing appearing is 0 as well. But as far as the events go, you have to include these events. So let me give you another example. Let's say there is a game between two teams, soccer game between red and blue teams. So the outcome, anybody who's familiar with soccer, there is the possibility of winning and tie. So there is the possibility of the red team wins and the blue team loses. And there is a possibility that, or the event that blue wins and red loses. There are also other possibilities that we have a tie. So these are 3 outcomes. The outcomes can be, if you, these are actually the outcomes. It's either red wins and R represents the event that red is winning, right? B is the event that blue is winning, and T represents the event that there is a tie. So these are 3 events. But there are more events. There is an event that blue either wins or ties. And you see here that I'm using or and now, right? So we'll keep an eye on these. There is the possibility that we have red wins or ties. there is an event that um, we have one outcome, and there is an event, I'm missing something here. Um, let's say the event that there is no tie. So it's either red wins or blue wins. And there is an event that any outcome, and the event that none, there is no outcome. So you see here that now when we consider probabilities, what is the probability that red wins? Well, if red is twice as strong as blue, we may consider that the chances of red winning is 60%. The chance of blue is winning 40%, right? Chance of tie is so and so, right? So we we'll have to discuss the events, then we'll assign probabilities to these events, right? Okay, so let's go back to the notes here and try to formalize what we just talked about. So omega is the set of all outcomes, and we will call that the sample space. So the sample space is the set that includes all the outcomes. So in case of tossing a coin, the sample space will be either head or tails. That's the two outcomes. If we toss a die has 6 faces, so and each face will represent a number, so the sample space will be either 1, 2, 3, up to 6, right? So we have 6 outcomes. In terms of a game, right, we will have either blue wins, red wins, or they tie. And we consider the events, which is each event will have a set of outcomes. Some outcomes appear in the event, some outcomes don't appear in the event. A phi is the event, the empty event. So every set here has an empty, has a phi, which is none of these appear, means that the probability of none of these outcomes appear. And the probability of an empty event is 0. And we have this notation here where the probability of an event is given as P curly squares and E. In the lectures and in many assignments, I will use P square instead of curly bracket just because they are easier to draw, right? Later we will see that the square brackets actually represent something. And we will use the square brackets actually more often. All right, so once we start talking about events, we need to discuss set operations. So these are, you have encountered them before in probability courses or statistics courses. So, and we will rely on them for the remaining of this chapter and the probability discussion in general. So first, every event has a complement. So the event of, let's say, blue wins, that's the event blue wins. So what is the complement of that event? Everything else, right? So this means that if I say, what is the probability that A does not win? This includes red wins or a tie. So all of the other events that doesn't include red is winning, right? And I have the concept of A and B. which is represented by the U here for union. So this is the event that both of them happen, or I should say either one of them happening, right? So the union is representing or. So what is the probability that A happen or B happen? That's given the simple U or union. What is the probability that A and B happening at the same time, right? So what's the probability that um, A wins and uh, a tie, right? Or A wins and B wins, or some. So of course, some of these events are they have a zero probability. But what is the event that both of them happening? Right? So we will use these events or we'll use these set operations quite often. So, and we will talk about each one of them in detail. But right now, let's talk about some concepts of or axioms of probability. So, when we talk about probability, the probability is understood as a number between 0 and 1, right? And keep that in mind. When we talk about probability, there is always a number between 0 and 1, right? If by any chance you do a calculation in an assignment or a quiz and you end up with a probability that's larger than 1, you must have made a mistake, right? It doesn't make sense. And you have to keep an eye on this because sometimes I get answers where the numbers are greater than 1. It should raise a red flag for you when you are when you are working with probabilities. The probabilities are always between 0 and 1. And we can translate the probabilities sometimes as a percentage. So, for example, the probability of 0.2, right, can be sometimes interpreted as 20%. So instead of from 0 to a 1, we'll do from 0 to 100. That's still okay, right? So if it's a probability, you are representing it as a percentage, so that's going to be from 0 to 100%, or the fraction multiplied by 100, right? The probability that the outcome or the entire sample space happening is 1, and the probability of nothing happening is 0. So if I go back to my previous examples here, the probability of the entire outcome appears, or any, not all of them at once, but any one of them appear. So the probability of the sample space here is 1. The probability of phi, or none of them appear, is 0. You consider these as or, right? So this is, for example, this example here, this means that red wins or tie, right? And so in this case, it's the equivalent of red wins or blue wins or tie. Okay, so now if we look at the previous example, we'll see that we have we can look at some events and see the relationships between them. One relationship in particular is important, which is the additive rule. The additive rule says that the probability of A happening or B happening is, which is the union, is the probability of A happening plus the probability of B happening minus the intersection between them. Right. So first we'll talk about it as a diagram or explain it visually, and then I'll talk about some examples. So let's say you have A event, you have B event, and you are looking for the probability of A happening or B happening. So that's the union. So if you look at the probability here, so you'll see that the probability of A is this black region here, and then probability of B is this red region here. But then if I do these two, I counted this middle twice, right? So I counted the middle part twice. So that's why I need to subtract it. So I will subtract the middle part. What is the middle part? The middle part is the intersection of A and B. So that's the event that both of them happen at the same time, which I have to subtract it because otherwise it will be counted twice. If you expand this concept more, you will find that, okay, so if the events are disjoint, so what is disjoint? Means that they are actually don't intersect. So A happen here, B happen here, and there is no intersection in between them. They don't meet. They don't have intersection. This means that I can say that PA or B is PA plus PB. And this part is equal 0, so I don't have, well, there is no, I mean, I subtract 0, so there is no change in the formula here. So if somebody gives you two events and they tell you they are disjoint events and ask you to find the probability of either A or B happening, then you will say that you can apply the second formula here. So let me give you an example quickly. So let's say, what is the probability of head is 50% or 0.5. The probability of tail is 0.5. What is the probability of A or B happening? Okay, so we know that these events, the event of head and the event of tail, are disjoint. Disjoint means that there will be no chance, no possibility of seeing head and tail at the same time. So now the probability of head or tail happening is probability of head plus probability of tail, and that's 0.5 plus 0.5 equal 1. And as that makes a lot of sense. Why? Because if I toss a coin, I am guaranteed either head or tail. So the probability of either head or tail is 1. What is the probability that neither head nor tail. So I represent that as the complement, right? So I have a probability of head or tail, or A or B. What is the other choices? We don't. So in this case, we actually introduce another concept, which is the probability of an event, or a complement of an event, is 1 minus the probability of the event. Why 1? Because we know that the probability is always between 0 and 1, right? So if I have an event that has a certain probability, and I want to find out what is the probability of the complement. So if this is 0.2, then everything outside must be 0.8. So when we add them together, we get 1, right? So in this case, 1 minus 0.2, we get 0.8. In this case, I know that the probability of the complement of A or B is 1 minus A or B. So now 1 minus 1 is 0. In other words, if I toss a coin, I will never get nothing. I will either get either head or tail, right? It helps when you think sometimes in probability you have to think in abstract terms, but then you have to also think about the actual um, interpretation of this, right? So you think about it in terms of, okay, so in reality, what does that mean? um, all right, so we can go over some examples, and we can go over, sometimes I'll come up with an example that's not mentioned here in the notes. um, But let's go over some of these that we have them here. So example, a job sent to a printer appears first in a queue with a probability of 60%, or you can interpret that as 0.6, and second in queue with a probability of 30%. Then the job appears either first or second in queue with a probability of 90. All right. It's crucial to notice that only mutually exclusive events, those with empty intersections or disjoint, satisfy the additive rules. If events intersect, their probability cannot be simply added. Okay, so what does this example tells me? It tells me that the printer, the job that was sent to the printer, cannot happen um, first and second at the same time. It's either the first or the second, right? So the two events, the printer job happens first or appears first in the queue or appears seconds, are mutually exclusive, or in another term, they are disjoint. So if the probability that it's first, probability that the job appears first is given as 0.6. The probability that the job appears second is 0.3. So now the probability that appears either first or second. So I can write it this way. So this means that the probability that a job, printer job, appears either first or second and this is equivalent to or, is by the additive rule is probability first plus probability second minus probability first and second. We know that this is 0, right? Because that's impossible. So now the result will simply be adding these two probability and we get 0.9. So that's what the second line here, second sentence tells me in the example. Okay. And I talked about the complement rule. So an example of the complement, if a system appears protected against a new computer virus with a probability 0.7, then the complement, which is not protected or exposed, is 1 minus 0.7. Or the common example, as I said earlier, if somebody tells you that there is a chance of rain tomorrow, which is 0.2, right? What is the chance of sunshine or no rain? Well, it's 1 minus 0.2 is 0.8. Right? We can expand on this idea by looking into the intersection of independent event. So now we talked about the additive rule, which is the, A or B. We use it when we need to consider A or B. But what if I want to consider the intersection? So now I want to consider probability of A happens and B happens at the same time. By the way, this symbol is easy to understand. So it looks like an and looks like an A, right? While the other one is supposed to mean or. So keep an eye on these things. Probability of A happening and B happening at the same time is represented by the intersection of two events. And I'm looking for this area in the middle between them. Now, if they are joint, if they are disjoint, like the heads and tails, or the first spot in the queue or the second, we have no intersection. This is 0. We cannot have heads and tails at the same time. Right? But there are other events that are actually, they can happen at the same time. Right? So calculating these events, the one way of calculating this is to use this formula here. What's the probability of A multiplied by probability of B, but only if they are independent. So there is a condition that A and B are independent. Independent means that there is no relationship in between. Right? They don't appear at the same time, or they don't depend on each other. What's the probability that there is a rain tomorrow and somebody wears blue? The two events may not be related. Somebody may argue, okay, well, maybe people like to wear blue less when it's raining outside. They like to wear bright colors. Maybe. If these events are independent, then we cannot use this rule. So they have to be independent to apply this formula. So if they are independent, then we can multiply their probabilities. All right, so example here, assume that network blackouts in previous example occur independently. So I think we talked about blackouts somewhere here in previous example, right? So what's the probability that blackout occurs on Monday or Tuesday? So the example, if I go back a few steps, says here, during some construction, a network blackout occurs on Monday with probability 0.7 and on Tuesday with probability 0.5. What's the probability that blackout occurs on Monday or Tuesday? So that's the or, and we calculated the or using this formula, and because they are mutually exclusive, so the two blackouts can occur not at the same time. So it's there is a blackout on Monday and there is a blackout on Tuesday. There are two disjoint, so we could assume that A and B um, is zero, but actually we can't, right? Because it is possible that a blackout appears on both days at the same time. So in this example, actually, we couldn't calculate A or B because this term at the last term is not zero. We cannot assume mutual exclusive. Right? So now, if we know that they are independent, a blackout can occur on Monday and can also occur on Tuesday, and the two events are independent. So we can calculate Monday or Tuesday by multiplying the probabilities 0.7 and 0.5. We get 0.35. And then we go back to the formula at the top and we calculate the probability that they happen either Monday or Tuesday. So now Monday or Tuesday equal probability of Monday, probability of Tuesday minus the probability of both, right? So 0.7 plus 0.5 minus 0.35, we get 0.85. So the 0.85 is the probability that the blackout can happen either Monday or Tuesday. So if I want to summarize all of this, I will say that the additive rule is written like this. All right, so usually we need some clues to solve this. If somebody tells me that A and B are mutual exclusive or disjoint, the same term, same meaning, this means that this is zero, and I can simply find this, right? If they are not mutually exclusive, if it is possible, as the blackout example, it is possible that blackout happens on Monday and also happens on Tuesday, so they're not mutually exclusive. So this means that I have to solve the last term here. I have to find what the last term is here. So my clue, if somebody says that, okay, there are independent events, So this means that I can calculate them this way. And then once I find this, I put it here and solve the additive rule, right? So for independent events, I can have the probability like this. And you will see that now we will use this concept in the next part, which is reliability. As I said, we need to use these, well, we study probabilities for a reason, and one of the reasons is to apply them in calculating the reliability of a network. So if we have a network, the networks consist of components that are connected to each other in various forms. So if I simplify things a little bit, so I can look into the components as they can be either connected in a serial form like this, or in a parallel form like the bottom here, right? So in a serial form, if I am sending a packet from the left here and I expect it to arrive in the right, all of these components have to work. If I have a disconnection in any one of these components, the packet will not arrive at the other end, right? So if I consider this example, I will say that the packet will go from left to right if if component 1 works, component 2 works, component 3 works, 4 works, and 5 works. So they all have to work. If I put that in terms of reliability, I'll say that the probability, so the probability that the packet goes from left to right so packet, let's say packet arrives, is the probability of 1 works fine and 2 works and 3 works and 4 works. So the probability that a packet goes from the start to the end depends on the probability that the component 1 works, the component 2 works, 3 works, and 4 works. And they have to work all at the same time, right? So that's why we put the AND here. Okay, so by comparing this to TOB, I have to find what is the probability of 1 works, 2 works, 3 works, and 4 works. So this is the, if I want to draw it in a diagram, this is the probability that all of these components work at the same time, or the intersection among them. So this is 1, this is 2, this is 3, and let's say this is 4. So I am looking for this probability here that all of them work, this shaded area here. Okay. If they are independent, if all of these components independent, so that they don't depend on each other on operation, each one of them has its own configuration, it has own power supply, they're not dependent on each other. We can assume that they are independent, and we can find that the probability is the probability of 1 is working multiplied by the probability of 2 is working multiplied by probability of 3 is working and multiplied by probability of 4 is working. If they are all let's say they are all the same components, same model of switch, same model of router, so we may say that their probability is the probability of 1 equal probability of 2 equal probability of 3 equal probability of 4, and we'll just give it a symbol like p here, right? Or any other symbol. So we could say that it's p to the power 4 here. So the packet will arrive, or probability of packet arriving correctly or without being dropped, is equal p to the power 4, where p, the small p here, is the probability that these systems, or one of these systems, works to the power of 4, right? So that's what we have here. So if I gave you an example of packet arriving, but if we generalize, we say, what is the reliability of the system? So the reliability in this case is the ability of the system to work, right? Whether it's delivering packet or delivering, or it's light, or whatever the job is, right? So the probability of the system working is the probability of all of its components working if they are in serial. And if the components have the same reliability or same probability of working, then we can simplify it by just taking one probability and multiply it 5 times, or the equivalent of ps to the power 5 in this case. Here is an example. A computer has had a hard drive that fails with probability 0.1. 0.1 or 1%, 0.01 in this case actually. If 2 other hard drives are added as backups, what is the probability of failure? If each one of the other hard drives has a 2% probability of failure here. That's actually gives us, or talks about the parallel systems. So let's skip that and talk about actually go here to the parallel system. So the second example, actually, parallel systems. So in parallel systems, we have this scenario where the system, the packet in this case, can go from left to right either through R1 or through R2. Right? So if R1 fails, it's still the packet can go to R2. In this case, the packet will not be delivered only if the two systems fail, right? So we always have two options. We can go through R1, we can go through R2. If one of them fails, we can still have a path to the other. But the system will fail completely if the two components fail. So parallel systems are good actually. We use them for redundancies. We use redundancies a lot in networking because actually redundancies give us multiple paths, and the system will always operate until all paths are exhausted, until we have no paths whatsoever, all the routes are exhausted. So parallel systems are used for redundancies and to calculate the probability of a packet going from left to right here, we have to look into different scenarios. So let's assume that a packet goes either through this component or through this component. And I'll ignore the source and destination here just to simplify. So the components, the packet can go either through 1 or through 2. So what's the probability that the packet arrives? So I can express that by saying the probability of packet arrives is the probability that 1 is working or probability of 2 is working, right? So if either one of them is working, the packet is going to be delivered. Compare that to the previous example where we have the packet has to can arrive only if 1 and 2 and 3 are working. Here it's or, either one of them. If either one of them works, we're good. Okay, so remember this formula, the additive rule. So this means that we have to have 1 or 2. So 1 plus 2 minus 1 and 2. I can do the calculations by if the two systems are independent, right? These two systems are independent. We assume they are independent. So we can solve this problem by saying right. So in networking, it's if nobody told you that they are independent, you can assume that these systems are independent and you can solve it this way. Okay, so that's one way to do this, but there is actually a simpler way. The simpler way is, well, and this becomes complicated, like this, solving this problem this way becomes complicated if I have multiple systems. If I have 3 here instead of 2, I have to do probability of 1 or 2 or 3, and this means P1 minus plus P2 plus P3 minus P1 and P2. So a 2 and then minus P1 and 3, and so it's actually gets longer and longer. So unless you have only 2 systems, this is not the recommended way to solve the problem. Instead, I can look at it from a different perspective. Right? So I can say that the probability of packet arrives between from this from left to right, right, is the probability that none of these fails, right? So the packet will arrive if none of these 3 fail. So how can I represent none of them fail? So I can say, what is the probability that all of them fail? So probability of 1 fails, that's the complement, and 2 fails, and 3 fails. That's the probability that all of them fail. Right? If you go back to the examples here, or to some of the formulas, see this one formula here? This is what I just wrote. E complement and E1 complement and E2 complement and E3 complement and so on is equivalent to E1 or E2, or so I will just use this. So this is 1 or 2 or 3 complement. They're the same. But I also said that this is 1 minus probability of 1 or 2 or 3. All right, so but actually this may lead us to the solution, but you can also take a look at this part without going over. So if you have this number, then you can go with this way. But look at this part again and see that if 1 and 2 and 3 are independent, then you can write this formula also as P1 complement, P2 complement, P3 complement. So this is 1 minus P1 multiplied by 1 minus P2 multiplied by 1 minus P3 . That's my probability of all of them fail, right? I'm not looking for the probability of all of them fail. I'm looking for the probability that all of either one of them succeeds, so the packet arrives. So the probability of packet arriving back to the top here is 1 minus all of this. So in parallel systems, it looks like it is more complicated to calculate the reliability. But once you get used to it, it becomes easy, right? So when you look at the serial systems, you need to find the probability that the system works, right? If you are looking for the probability in or the reliability of parallel systems, you are calculating the or you're using the reliability of the system fails and then take the complement. So it has been, I took a long route to arrive here, but I hope that this explains why we're getting there. So here, the success or the reliability of the network is 1 minus the probability of all of them fail, all the components fail. So we can start by looking at the probability of the component fails. Since the components usually independent, we can take the complement of each one of these probability of failures and multiply them. Okay, so let's take example here. Go back to the hard drive example. So the hard drive example says that the computer has um, 3 hard drives. So the main hard drive, and then we have a backup 1 and a backup 2. The failure, the probability that the hard drive fails is 0.1. The probability of the backup backup 1 fails, is 0.2, and the probability of backup 2 fails is 0.2, right? So what is the probability that the system works? Or what's the probability that the system doesn't work? So the probability that the computer works is represented by a parallel system. So it's like our network. Let's say that the computer or the data will be retrieved from the hard drive either through the main hard drive or one of the backups. So this looks like a parallel system. Right? And for the computer to work, it will work as long as either one of them is working, either one of the hard drives is working. So it is the probability 1 minus all drives fail. Right? So this means that it's the probability that the hard drive fail, the main hard drive fail. I'm gonna go for the longer steps here. Either the main hard drive fail and B1 fails and B2 fails. So they have to all fail for the computer to fail. This means that we have, because they are independent, and in this case actually they gave us the failure, they gave us the H complement, so we can say 1 minus 0.1 multiplied by 0.2 multiplied by 0.2, right? And the result will be written here, which is 0.99. So that's the probability that the system works. So lots of tutorials and examples would get you used to this. But notice that while I'm talking, I use to represent events here. So when I say probability of packet arriving, that's an event, right? Probability of one complement here, that's representing the event that the first system works and the second system works or doesn't work and the third system works or doesn't work. So these are events. So one of the things that you should get used to is to list down the events that you are working with and define them. So when you say in a parallel system like or a serial system like this one, S1, S2, S3, and so on, you can define your events and say S1 is the event, or you can define the events here as S1 first system works, S2 is second system works, and so on, right? So once you define your events, you can start saying that the probability S1, so now it's understood that the probability that the first system works, and you assign the probability. So that will, first of all, it will make you uh, understand the problem better, right? And in an assignment or a quiz, it will give me an indication that you are going through the steps correctly, right? So when you write your work, if you write formulas, you may get a chance that everything works fine. I'll say, okay, the result is correct, and I'll give you full mark. But when you start by going step by step, writing your events, writing your steps, even if you make a mistake, I'll understand that you are working correctly, or because sometimes the calculations go wrong, right? The calculator, people in a hurry, um, for any reason, you may get the output wrong. But if you go through um, the problem step by step, then it's for you it's a better chance to arrive at the end results correctly. And if you made a mistake, you will at least make a mistake at the end. Okay? So keep that in mind, and we will practice this in the tutorials more often. Okay, let's talk about different topic now. So if we go back to the notes here, there is the um, topic of permutations and combinations. So earlier on, I talked about events and the sample space. So the sample space includes all the outcomes, and the events, each event will include a set or some of these outcomes. So the event may include an outcome or doesn't include an outcome. Okay. So to explain this more, let's say we have a die toss, right? And the outcome will be 1, 2, 3, 4, 5, 6, right? So and the sample space will be 1, 2, 3, 4, 5, 6. And as before, there is the event that 1 appears. So event 1 is including this and doesn't include the rest, right? The event of 2 appears is the event of this appearing, 2 appearing, and nothing else. So you consider it a binary, right? And there are 2 to the power 6 possibilities here. There are also some interesting events, like the event of even number. So that is the event that includes 2 or 4. And as I said, when you look at them, you think about or, right? Because if you think about and, then it's impossible to have 2 and 4 and 6 at the same time, right? The event that there is an odd outcome, odd number, is this one. The event that you have a number above 3 is this one. 3, 4, or 5, or 6. All of these events that lead to something that's above 3. And also, if you think about them, like the OR versions of them as well, right? All right. Because of that, and because we have a large number of events, we start thinking, okay, if I want to calculate the probability of, let's say, the event that even number appears, so the uh, probability that even number is the probability of 2 or probability of 4 or 6. And remember, when you say A or B, it's PA plus PB minus A and B. Because we know that in this case, we cannot have 2 and 4 at the same time, so they are mutually exclusive, and we can simply say that their probabilities are P2 plus P4 plus P5. And because each one of these probabilities are equal, the probability of 2 appearing is equal to the probability of 4 equal to the probability of 6, which is all 1 over 6. So that's equal to 3 over 6 or half or 0.5. Okay, so that leads us to something interesting, which means that if we have this situation where all the probabilities are the same, right? Then we can simplify things a little bit and say that if if all the outcomes have the same probability, then the probability of any event that we saw earlier, is the probability is the equal to the number of outcomes that are favorable, that we like, divided by all the number of all the outcomes. All right, so let's go back here and say the probability of even number. So how many even numbers we have? 3, right? 2 and 4 and 6. How many outcomes overall? We have 6 outcomes. So now we get to the same result. So we don't have to go through these steps. We just, because no, we know that all the outcomes have this, all the events uh, so all the outcomes have the same probability. So if I want to find the probability of specific events, I will find that how many outcomes in that event and divide it by the number of all outcomes. All right, so tossing a die results in 6 equally likely possible outcomes. Since all the outcomes are equally likely, we can find that we looked at even numbers. We can do the same thing for odd numbers. But how about if I want to find the probability of a number less than 5? Right? So how many numbers are less than 5? There is 1, 2, 3, 4. divided by 6, we get 4 out of 6, or 2/3, or 0.666, right? So that's the simplest, that's the main um, result that we get when we have a set of outcomes that they have the same probabilities. In many situations, we have this the concept of selecting something out of a set, right? Um, and it comes in many examples. So let's say I go to I buy components, computer components, hard drives, right? I buy a group of them, large group. Some of them are defective. So sometimes the question says, well, if you buy 15 hard drives and you select 5 of them to build a computer, what is the possibility that 1 out of 5 is is damaged, right? So some of these examples require us to consider the concept of permutations and combinations, also the concept of replacement and no replacement, distinguishable and indistinguishable, right? So it's better to go over this with some examples. One of the examples is passwords. So when we select a password, think about how many passwords you can create out of um, 10 numbers, right? So if you have 10 numbers, the Arabic numbers, which are 0, 1, 2, 3, 4, 5, right? And you want to select a password that has 3 digits. So what are the possibilities of creating 3-digit password out of 9 characters, nine numbers? So now we're not talking about probabilities. We're just talking about counting. We need to count how many possibilities out there. So if I look at this series of numbers, I have 10. Initially, I will select 1 out of these 10. So I may select 2, I may select 3, I may select 4. So I have 10 different possibilities of selecting the first digit. So that's my first digit. All right. And what is the possibility of selecting the second digits? If somebody tells me that I am free to select the same digit twice, right? So I can create a number using any digit I want. There's no restriction. So the second digit will be also, I have 10 possibilities. So I have 10 simples here to choose from. Same thing for the third digit. I can select any of these 10 digits. So how many possibilities out there of selections? It's 10 to the power 3. That's 1,000 different possibilities of selecting digits. Okay, so now what I did here is equivalent to, imagine these numbers as physical numbers, right? Physical something, uh, printed them on paper, and I selected one digit, put it in one, and put it in the first spot here, and then I put it back, and then selected randomly, maybe out of a bag without seeing what the numbers are. I put it back in the bag and select another random number. I put it in the second digit, put it in the bag again, and blindly select another digit and put it here. So I may end up with a number like 3, 6, and 3, or 1, 2, and 0, or any number. So the possibilities there are 10 to the power 3, and every time I did this, I replaced the number back in the bag and selected it, or it is possible to select it again randomly. All right, so that's the concept of replacement. Okay, what is the concept of no replacement? Okay, so let's do the same experiment here, but the condition is once you use a digit, you cannot use it again. So once you put all these digits, numbers, in a bag and select one of them, and then that one that you select, you cannot use it again, so you throw it out, right? So that's with replacement. And this is without. So you have the same 3 digits. First, you have 10 options you pick from. So you have 10 possibilities. But then, once you select a number, you cannot select it again. So in the second round, you have only 9 possibilities. In the third round, you have only 8 possibilities. So now you have the number of possibilities is 10 multiplied by 9 multiplied by 8. If you want to formalize or formalize this, so here we actually did 10 to the power n, or 10 to the power k, or you choose a number, which n represents the number of the length of the password, right? Here, this is equivalent to n factorial minus 10 minus n factorial, right? How? All right, so n factorial is 10 multiplied by 9 multiplied by 8 multiplied by 7, right? While 10 minus n, which is 7, so 7 factorial is, so that cancels this. We get 10 multiplied by 9 but multiplied by 8. So that's why I wrote it this way. All right, so that's the reason behind this. All right, let's go back to our example. So here we have 4-letter passwords, and we have 26-letter English alphabet. So if I am allowed to select any letter from the English alphabet and reuse it, so now we have the possibilities, how many possible 4-letter passwords I can create is 26 multiplied by 26 multiplied by 26, and so on, to the power of 4. So that's the number that I get, right? We'll call these permutations. So the permutation is without or with replacement is given by this formula or this simple. So the permutation nk, n is the possible selections and k is the distinguishable objects, right? So what are the distinguishable objects? We know that the digits 0, 1, 2, 3, 4, they have meaning, so they are distinguishable. So the number 0, 1, 2 is different than the number 2, 1, 0. The letters A, B, C as a password are significantly different than the letters or the password C, A, B or C, B, A, right? So their order, or they're distinguishable, and their order means something. So we cannot say that A and B and C is the same as C, B, and A. So we consider that distinguishable. If they are distinguishable, then they're the we count ABC and CBA as two different things, right? And the permutations or the number of possibilities is given by uh, n, p, n, and k, and n here is the number of possibilities, k is the number of objects that I selected. In the case of the password, the number of possibilities 26 characters, the number of objects that I want to select in each is 4. All right. With replacement, I showed you this. So n factorial divided by n minus k factorial. Here, if I want to rewrite this, so n becomes 10 and k is 3, and the permutation of n k is r is for replacement, right? So it's n to the power k is 10 to the power 3 or 1000. Here also using the same notation, n factorial divided by n minus k factorial, so that's 10 over 7, which gives me 10 multiplied by 9 by 8, right? Okay, so that's permutations. How about combinations? In the combinations, we also select something out of a large group, but the order is not different. The order it doesn't matter, I mean. So let's say I want to select 3 groups out of the class. The class is 28 people, and I want to select 3 of you to help me with something, right? In that case, I'm going to select randomly. It doesn't matter if Ali and Komar and Mike happen. Doesn't matter what the order is, right? I'm just going to select 3 of you, and the order of the selection is not important. So in that case, I will use the combinations, and I'll represent the combinations with the capital C, N, and K. N is the total number, the set of all objects, N, and k is the number that I selected. So in a class of 20 students, how many ways there are to select 3 students to represent the class in a school-wide competition? Right, so if the class is 20 and I pick 3 at random, so I'll use this formula 20 factorial divided by 20 minus 3, and you'll see here the multiplied by 3 factorial. So I get 1140. In the in the example of selecting people out of the class, when I select somebody, I'm not gonna put him or her back and select again, right? I'm gonna select only once, right? So when I select 3 out of 20, I've picked one, and then I pick another one and pick another one. I'm not gonna put them back, right? Uh, so if I want to have a situation where I put a replacement, then I'll use this formula here, which is less common, and I cannot think of good example of that. So there is no example here in the notes about that. But the formula will be uh, choosing. I guess you have to distinguish between the two by putting R and no R here. So k plus n minus 1, choose k, and you get this formula. So this table will show you the permutation with replacement and without replacement, combinations with replacement and without replacement. Right? So use the general recommendation, general rule is to use permutations when the objects are, when the order is important. If the order of the objects is important, use permutations. If the order of the object is not important, so it doesn't matter what the order is, use combinations. Okay. So the combinations and permutations help us count. They just help us find the count. But remember, we're talking about probabilities, right? So eventually we will need to use probabilities. So we'll find the probabilities by the general idea that the probability is the number of favorable events divided by the number of total events. So we saw earlier that the probability of even number is the probability of 2 and 4 and 6, so that's 3, divided by the probability of all of the other outcomes, which is the count of the other outcomes, which is 6, so we get 0.5. Right? In many other examples, we need to use these formulas to counting them in our head. It's not going to be possible, so we need to use the combinations and permutations. So let's take an example here. There are 20 computers in a store. Among them, 15 are new and 5 are refurbished. 6 computers are purchased for a student lab. From the first look, they are indistinguishable, so the 6 computers are selected at random. Compute the probability that among the chosen computers, 2 are refurbished. The total number of ways, so the answer will be, right? So let me draw this. So remember, we have 20 computers. 15 are new and 5 are refurbished. Right? So let's visualize it. We have um, 5 are refurbished and 15 are new. So that's 5 and another 5 and another 5. So total is 20. And I'm picking 6 at random. Right. I don't know. They look exactly the same from the outside. So I'm picking something at random. I'm picking 6 at random. So the question here is, what is the probability that among those 6, 2 are refurbished? So if I'm picking 6 here, what is the probability that 2 are refurbished? So if I, what are the possibilities? There is a possibility that I'll get all 5 refurbished, and then 2 and then 1 new. There is a possibility also that I'll get 5 new and 1 refurbished, and there is a possibility that I'll get 2 refurbished and 4 new. All of these are possible. I am looking for the probability, specific probability, that there are 2 refurbished and the other 4 are new. That's the probability that I'm looking for. Okay, is the order important in this case? No, it's not. It's not important. I mean, it doesn't say that the 2 have to be like. It doesn't matter whether the order I pick is green, green, red, green, and red again. So the order is not important. So if the order is not important, I immediately think of combinations. Okay, but what are the numbers here? So I need combinations with replacement, because once I pick a computer, I'm not going to put it back. So with replacement, without replacement, I mean. So what is my N and what is my K? So here, to get 2 refurbished and 4 none or brand new refurbished, the count, how many possibilities out there, right? How many possibilities out there for 2 refurbished and 4 new? This would be my favorable outcome. All right, so I have 5 refurbished. I'm looking for the number of ways that I can pick 2 out of these 5. So 5, picking 2, and also the number of picking 4 new out of 15. So that, by the formulas, that's 5 factorial divided by 3 factorial, 2 factorial, multiplied by 15 factorial divided by 11 factorial, 4 factorial. That's my the number of favorable outcomes. So how did I do that again? All right, so it's like the digits where I have 10 digits and I had to pick 3 of them, right? Here I have 5 refurbished and I'm supposed to pick 2 of them. It doesn't matter the order, I just need to pick 2. So how many ways I can pick 2 out of 5? So I have 5, I can pick the first and the second, or I can pick the first and the third, or I can pick the second and the fourth. So how many possibilities out there? The number of possibilities out there is 5 factorial divided by 3 factorial, 2 factorial. So if you calculate this, so that's 5 multiplied by 4 multiplied by 3 multiplied by 2 divided by 3 multiplied by 2. Right, so these cancel these 2, so you get 10. Right, and the same calculation you do it here. So at some point you need probably to use a calculator. So the factorial is here, so 15 factorial divided by 11 factorial divided by 4 factorial, you get this number here. So that's my favorable or my favorable outcomes. But what is the total outcomes? So the total outcome, the total number of ways I can pick 6 out of 20. In this case, I don't care what, like, I'm just picking 6 out of 20. I don't care what color they are. I don't care what status they are in. So that means that I am picking 20, choose 6, right? So 20 choose 6 is 20 factorial divided by 20 minus 6, which is 14 factorial divided by 6 factorial. So I will end up with this number here. So the probability that I will pick 6 and there are 2 of them refurbished is 0.3713, right? After doing all of these divisions. Right. Okay. So now we get to the topic of conditional probability. In the conditional probability, we saw earlier that we looked at the situation we have independent events, right? So when we saw independent events, we saw that for an independent event or 2 events, B, A, and probability of A and B, if they are independent, we can calculate their probability as PA or PB, right? So 2 events, and I'm looking for the intersection here. So the probability of the intersection is PA multiplied by PB if they are independent. Some events are not independent. Actually, some events are dependent on each other, right? So if you have flights, one departs and arrives, and then another one, you take another flight and then it departs and arrives. what are the probability that you will lose a connection or you won't be on the second flight if the first flight arrives late? Now, of course, these are two dependent events. The higher probability that the first flight arrives late, the higher chance that you will not be on the second flight. In networking, think about sometimes, let's say we assume that reliable systems or redundant systems are independent, totally independent. But sometimes, let's say you are sending traffic through router A and B, so you're splitting the traffic. But if A fails, B will take more load. So now the probability of B failing increases. So the two, like you cannot consider the two events are totally independent. So again, while this is a little bit early to talk about, but sometimes in the design, you have to think about the possibilities like this. So for simplifications, for simplicity's sake, sometimes we assume that the systems are independent and they fail independently. In reality, sometimes one system fails, the other system is likelihood to fail is increasing because of increased load or increased let's say if a security attack, one system fails because of security attack, the other system may also be subject to attacks as well. All right, so we represent these events as probability of A given B. So let's say that what is the probability of A happens if B happened? Right. Okay, so in that case, it is given by this formula. So the probability of A happening if B happening, and remember A given B is totally different than this notation here, right? So I see a lot of students using this notation. Maybe the keyboard does not support this vertical line, or I don't know the reason, but I don't focus too much on it, but because it's not correct. The notation is not correct. This is supposed to be a vertical line. That's the notation of dependence, or the conditional probability, I should say. All right, so this is equal to BA intersection B divided by PB, right? So the red, the black region here divided by the red region here, right? So probability of A given B is the probability of intersection, or A and B divided by B. You get some interesting results out of this. So if somebody tells you that A and B are dependent on each other, so you could, so A intersect B, or A and B are, or is A given B multiplied by PB. So what happens if somebody tells you that give me the probability of A given B if A and B are independent? So if B, A and A given B, if the two of them are independent, is exactly as BA. Which means that this formula becomes A given A intersect B equal BA BB, which is the same as here, right? Okay, from that we get to the Bayes rule or rule, and by manipulating the formulas a little bit. So let's take a look at this formula again, or the equation. What we're trying to find is probability of B given A probability of B given A is the same, well, it can be written this way: probability of B intersect A over probability of A. But we know that A intersect B is the same as B intersect A, so or can be written this way. All right. So this, we found it before, and so we can write it as P, I'm copying this part here, so P A given B, probability of B so I'm getting one conditional probability by using the other. So that's one lesson, but I can expand on that a little bit and get to something called the law of total probability. Right? To understand this, we have to look at this example here, or this figure. Let's assume that we have an event A. The event A itself is intersecting with multiple events, B1, B2, B3, B4. So A is actually these two slices, all these slices. All right, so A, without going too further here, so here we have example of A and B. Let's take a look at the situation where we have A is actually intersecting with B, so this is A, and this is B, and this is B complement. So I can represent A as PA as probability of A intersecting with B plus PA intersecting with B complement. And if I look at top here, I see that P or P and B is the conditional probability presenting like this. So this is P A given B multiplied by the probability of B plus PA given B probability of B complement. So I can write the top formula again as probability of A given B, probability of B divided by PA given B So now I represented this is the law of total probability, which applies in this scenario. It applies because every event has a complement, and the two events, the event and its complement, are mutually exclusive, right? They are disjoint, so there is no intersection between the event and its complement. So we can represent the denominator here as a sequence of disjoint events. In the general case, if A event is intersecting with multiple events here, I can say that the probability of A equal probability of, let's say this is B, C, D, E, F, for example. So I can say A given B, probability of B plus A given C, probability of C, and so on. As long as these events are mutually exclusive or disjoint, they don't have intersection. And this is what I call the law of total probability. All right? Okay. So now we considered all of these scenarios. Let's go and take an example. Okay, so we have an example here that says 90% of flights depart on time, 80% of flights arrive on time, 75% of flights depart on time and arrive on time. And then we have certain questions here. You are meeting a flight that departed on time. What's the probability that it will arrive on time? And then you have met a flight and it arrived on time. What's the probability that it departed on time? And then are the events departing and arriving independent? All right. So this is one of those questions that are wordy and you have to dissect it. So the first thing, as I said earlier, to recommend is to just define your events. So In this case, we defined A as the event of flight arriving on time. D is flight departing on time. So that's defining the events. And then we'll see what is the probability. So probability of, it says here, 80% of flights arriving on time. So probability A is 0.8. 75% of flights depart and arrive on time. So PD, this one is given 70%, 75% of flights depart on time and arrive on time. So that's PA and D. And there is also the 90% of flights depart on time. So that's PD equal 0.9. So to answer the first question here, you are meeting a flight that departed on time. What is the probability that it will arrive on time? So this is a conditional probability. So it's asking you if it departed on time, what will be the probability that arrives on time? So this is A given D. A arriving given D departing. So here we have PA given D by the basic formulas that we saw earlier is PA intersect D divided by PD. All the numbers are there, so P and D is given as 0.75, PD is given as 0.9, so we just need to divide the two numbers. So that's straightforward. The second question is the flight arrived on time. What's the probability that it departed on time? So we are actually looking for the opposite here. So what is the probability that if it's departed on, we know that it arrived, right? We know that it arrived. So what's the probability that actually departed on time? So this is PD given A. What's the probability that it departed on time if we know that it arrived on time? So again, by using the same formula as before, PD intersect A over PA. These P intersect D and D intersect A are the same. So we're using the same numbers and we get 0.9375. Finally, we need to know if the two, probability of A and probability of D, are independent, right? So how do we test if they are independent? We know that if they are independent, then PA intersect D, arriving intersect departing, is PA PD, right? So we know that. So we just need to test if this is actually, we know this one is 0.75. We need to figure out this one. So if we figure it out and we compare them, we know that if they are independent or not. So, but the problem here is, do we have probability of, yeah, we do, so there is no problem. So we just need to check if point A multiplied by 0.9 is actually 0.75. We know that's not 0.75, right? So and we also know that PA, if they are independent, PA given D is supposed to be equal to PD if they are independent. And also if they are in DA, P, D given A is supposed to be equal to, sorry, this is supposed to be A here, and this is supposed to be D. Let me clean this up a little bit. So this is 0.75, but this is arrival is 0.8, and this is 0.75, and this is 0.9, so they are not equal. And also, if I multiply 0.8 by 0.9, I'm not going to get 0.75. All right, so I did all of these tests and they all failed. Right? So there are multiple ways to do the testing. I can compare these two, right? If they are independent, then this number is supposed to be equal to this number. Also, if they are independent, BA given D is supposed to be exactly like BA, and BD given A is supposed to be exactly like BD. Right? So this is how we test independence. Okay, so that concludes the chapter. There is a summary here, and there are some tutorials that we will do in class. So I hope this is useful, and you can go back and review the recording, and let me know if there is any take note. Let me know if there is something that I said wrong, or if there is something that's not clear, and this should help you with the study. All right, thank you, and I will see you in the next recording.